Let's investigate some fascinating prime numbers which are related to the Y2K38 problem. Consider the quantity 2 to the power of 2 to the power of 5 minus 1. So this quantity is 1 less than 2 to the power of 32. 2 to the power of 5 is 32. This quantity is the maximum value that can be stored using an unsigned 32-bit integer. Is this quantity a prime number? The answer is no. In this video, we're actually going to find the prime factorization. We can begin finding the prime factorization by making the following observation. This quantity is equivalent to 2 to the power of 2 to the power of 4 plus 1 times 2 to the power of 2 to the power of 4 minus 1. So why is this the case? If we take this plus 1 and this minus 1, and we multiply them together, that explains this minus 1 over here. And we also have a cancellation. If we take this plus 1 times 2 to the power of 16, that cancels with minus 1 times 2 to the power of 16. And if we take 2 to the power of 16 times 2 to the power of 16, then we get 2 to the power of 16 plus 16, which is 32, or 2 to the power of 5. And 2 to the power of 4, that is 16. Now, we're going to continue factoring this value over here. But before we do that, let's represent the value 1 less than 2 to the power of 32 in hexadecimal. So this quantity can be represented in hexadecimal. We're going to use the prefix 0x to indicate that we're dealing with a hexadecimal value. And we can write this as F, 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 F. So that's 4 Fs. And then F, 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 F. So that's 8 Fs in total. So in binary, this would be 32 ones. And we can also write this quantity as 2 times m sub 5 plus 1. So this is a double Mersenne prime, and we will explain this notation later in the video. And another way that we can represent this quantity is with its prime factorization. And this prime factorization can be written as the product, we're going to use pi notation for the product, over the index n going from 0 to 4, and we have f sub n. So this notation is referring to Fermat primes. And we're going to discover 5 Fermat primes in the prime factorization of this quantity. So we've got some very fascinating prime numbers. Now, do not confuse this f with a subscript with this f over here. So this lowercase f I'm using to represent the value in hexadecimal. And this over here is representing a prime number. And here we have 5 prime numbers, and they are specified using this index n. So now let's continue finding the prime factorization. Now, first of all, we can identify this factor as a Fermat prime. It actually corresponds to n equals 4. So we'll take this value over here. We can label it as f sub 4. And Fermat primes have the format where there is 2 to the power of 2 to the power of n, and then we add 1. So it's 1 larger than that power of 2. And the exponent is also a power of 2. So this is f sub 4. And we can write it in base 10 notation. This is 65,533 7. And this other factor over here, that is 2 less. So it is 65,535. So f sub 4 is a prime number. But this other factor over here with a minus sign, it is not a prime number. We can actually continue this pattern and we can continue the factorization process. So let's take this factor with a minus sign and let's break it up into 2 factors. We can break it up into 2 to the power of 2 to the power of 3 plus 1 times 2 to the power of 2 to the power of 3 minus 1. And we can identify this factor with a plus sign as f sub 3. So we have 2 to the power of 2 to the power of n plus 1 again. So this is f sub 3. And in base 10 notation, we can write this as 257. So 257 times 255 is 65,535. And we can take this product over here and we can write it in hexadecimal notation. So this is 0x2, this prefix indicates that we're writing a value in hexadecimal. And then we have F, 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 F. So that is 4 Fs. In binary, it would be 16 ones. So you can see over here we have 8 Fs, which is the same as 32 ones in binary. And we can continue this process. So we identify that this is a prime number. It's a Fermat prime. And over here, this is not a prime number. We can break it apart even further. We can break it apart into 2 to the power of 2 to the power of 2 plus 1 times 2 to the power of 2 to the power of 2 minus 1. And then we can identify this factor with a plus sign as another Fermat prime. And this Fermat prime is f sub 2, which is 17. And that means this one over here is 15. So this is 255, which is equivalent to 17 times 15. Now, what is 255 in hexadecimal? We can write that as F. And in binary, this would be 8 ones. So 8 ones in binary is equivalent to 2 Fs in hexadecimal. So this value over here is 255, and we can break that up into 17 times 15, and then 15 can be broken up into another set, which is 5 times 3. So we can see that underneath. We can write this as 2 to the power of 2 to the power of 1 plus 1 times 2 to the power of 2 to the power of 1 minus 1. And we can identify this is 5 over here. So we have 2 squared, which is 4, plus 1, and that is 5. And we can also label it as f sub 1. That is 5. And 5 times 3 is 15. And what is that in hexadecimal? In hexadecimal, it is a single f. And what about in binary? We can use the prefix 0b to indicate that we're representing this in binary. In binary, this is 1, 1, 1, 1. So we have 4 ones in binary. We're just a single f in hexadecimal. And that represents the quantity 15. So this is 15 over here, and we can break up 15 into 5 times 3. And let's repeat this procedure one more time. So let's break this up into 2 to the power of 2 to the power of 0 plus 1 times 2 to the power of 2 to the power of 0 minus 1. So this value over here is 2 plus 1, which is 3. So we can identify this as the Fermat prime f sub 0. And we can also identify it as another type of prime, which is a Mersenne prime. And it is actually m sub 2. So this quantity is equal to 3, and we can write that in binary as 1, 1. So 3 is 2 ones in binary. And observe that this other factor over here is 2 minus 1, which is just 1. So this is 1 times 3, which is equivalent to 3. And we can terminate over here. We found all of the prime factors. So f0 times f1 times f2 times f3 times f4 is equivalent to 1 less than 2 to the power of 32. That is the prime factorization. And that is condensedly written using this pi notation for multiplication. So we have this index n, which goes from 0 up to 4. And that includes these 5 prime numbers over here. And we can also see the relationship between these values and their hexadecimal representations. You can see that you can represent them in binary or in a more condensed hexadecimal format. So we terminate over here because we have reached 1. So we can see here we have 1 times 3, that gives us 3. And then this is 3 times 5, which gives us 15. And then 15 times 17 gives us 255. 255 times 257 gives us 65,535. And then if we multiply 65,537 times 65,535, we get this quantity, which is 1 less than 2 to the power of 2 to the power of 5. So that's the prime factorization. We've seen primes that have this format. These are called Fermat primes. But not all numbers that have this format, where it's 2 to the power of 2 to the power of n plus 1, not all of those values are prime. So these are very special values, and that's why they're called Fermat prime numbers. Now, let's also consider another interesting type of prime number, which is called a double Mersenne prime. So we've used this notation over here, m sub 2. A Mersenne prime has the format where we have 2 to the power of a prime number minus 1. So instead of a plus 1 over here, like for the Fermat primes, we have a minus 1. So this is 2 to the power of 2. That's why we have this subscript 2. And then we're subtracting 1. So in this format, we can see that 3 is a Mersenne prime. And in this format, we can see that 3 is a Fermat prime. So 3 is very special because it's both a Fermat and a Mersenne prime. It's a very interesting case. Now let's examine double Mersenne primes. So first, we'll define the general case. So in general, if we have the notation m sub p, where p is a prime number, and we're using this to denote a double Mersenne prime, it's going to have the following format. We're going to have 2 to the power of 2 to the power of p minus 1 inside the exponent. So this minus 1 is up here in the exponent, and then we have another minus 1 outside the exponent. So you can see that this subscript, m sub p, that indicates the exponent over here. It's 1 less than 2 to the power of p. So we're using another Mersenne prime to define this Mersenne prime. So it's a Mersenne prime within a Mersenne prime. And we call this a double Mersenne prime. And we're going to see 4 examples of double Mersenne primes. And one of those examples is related to the Y2K38 problem. So let's consider the smallest example first. We'll set p equal to 2. So we saw what happens when you have p equal to 2 over here if it's just a single m sub p, so just a single Mersenne prime. So we're going to consider m sub 2. Now we know what m sub 2 is. That is 3. So we can write this as m sub 3. And this is 1 less than 2 cubed. which is 7. So we can write this as 7. And in binary, 7 is 1, 1, 1. So it's 3 ones in binary. So that's the first example of a double Mersenne prime. Let's have a look at the next example, m sub 3. So this can actually be written as m sub 2. We can identify that m sub 3 has this format over here. So here we have a triple Mersenne prime. It is a double Mersenne prime and a triple Mersenne prime. And we can also write it as m sub 7. So we have a 7 over here, that's equivalent to m sub 3. And what is this? This quantity is 1 less than 2 to the power of 7. So that is 127. In hexadecimal, we can write this as 7f. That is the hexadecimal representation. And in binary, this would be 7 ones. So that is this value over here. And now let's have a look at a very interesting double Mersenne prime. That is this one over here that is relevant for the Y2K38 problem. We can write that as m sub 5. What is m sub 5? That is 1 less than 2 to the power of 5. What we're dealing with over here is 31. That's the quantity that we're dealing with. So we can write this as m sub 31. And in hexadecimal, we can represent this as 7 f, 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 f. So we have a single 7 followed by 7 f's. And in binary, this would be 31 ones. So that is the value that we have over here. If we double this value, which is 2 to the power of 31 minus 1, and then we add 1, we will get this value that we saw in the beginning, which is 1 less than 2 to the power of 32. And why is this value special? That is because m sub 5 is the maximum positive value that can be stored using a signed 32-bit integer in the 2's complement format. So that's why this value is very important. It's very relevant for understanding the Y2K38 problem. So over here we have the maximum value that we can store if we have a signed 32-bit integer in the 2's complement format. And over here, we have the maximum value that we can store if we use an unsigned 32-bit integer. These are very important values in computing. And now let's just have a look at one more example of the double Mersenne prime. So we're going to have a look at m sub 7. So this is a double Mersenne prime, but it is also a triple Mersenne prime. So we can write this as m sub 3. And it is also a quadruple Mersenne prime, because we can write it as m sub 2. So it's a Mersenne prime within a Mersenne prime within a Mersenne prime within a Mersenne prime. It's a very interesting pattern. And we can also write this as m sub 127. So in binary, this would be 127 ones. It's a very large number. So we have seen an example of a quadruple Mersenne prime. We have seen 2 examples of triple Mersenne primes. And we have seen 4 examples of double Mersenne primes. So you can see this nesting phenomenon that is happening over here. And we can unpack this by identifying that m sub 2, that is equal to 3. And then m sub 3, that is equal to 7. And then m sub 7, that is equal to 127. So in this video, we saw 4 examples of double Mersenne primes, and we saw 5 examples of Fermat primes. These are the only known examples that satisfy this format. So if you find any other examples of Fermat primes that are larger, or any other examples of double Mersenne primes that are larger, please put them in the comments, because that would be a very interesting discovery. So we've seen that these prime numbers have practical applications in understanding the Y2K38 problem, and they're also fascinating. We can see this fascinating prime factorization over here. So even though this value is not a prime number, the prime factorization is fascinating. And it's related to this other prime number over here, and that has a very interesting format. You have these nested prime numbers, where you're using Mersenne primes as exponents in other Mersenne prime definitions. But just keep in mind that if a number has this format, or this format over here, it's not guaranteed to be a prime number. In order for values to belong to these groups over here, they have to be both prime, and they have to satisfy these very special formats. So this very special format, if we set p equal to 5, we get that very interesting number, which is the maximum positive value that can be stored using a signed 32-bit integer in the 2's complement format. And understanding that value helps us understand the cause behind Y2K38.